So we are dealing with the fourth problem in this series, and the fourth problem is problem 3.22. The problem is stating each of the two long parallel threads carries a uniform charge lambda per unit length. The threads are separated by a distance L. Find the maximum magnitude of the electric field strength in the symmetry plane of the system located between the threads. So again, when we start approaching the problem, the first thing that we will do is we will try to explain the system by drawing a necessary diagram. So this is the necessary diagrammatic arrangement for the situation which the problem is discussing. So over here what we have is a wire having charge density lambda or lambda charge per unit length. This one is also the same wire. So this is a positive charge wire, so it is going to have an electric field which is directed away from it, which we are representing over here as E naught. Similarly, this charge which is also positively charged will have electric field directed away from it, having the same strength E naught as the separation between them from the point P is same. So over here these are the two aspects that we have noted out in the plane of this system. So over here the separation is L, so we cut this as L by 2 respectively, and from this distance x we are considering a point P which is at a distance r from the two infinitely large threads. So over here we can say that E net can be written as 2 E naught cos theta. So E naught cos theta due to first wire, and then again E naught cos theta due to second wire. So we can write E net as twice of, now this E naught can be written as lambda upon 2 pi epsilon naught r followed by this cos theta. So cos theta can be written as base by hypotenuse, so x by r. So we get the E net value as lambda upon pi epsilon naught, 2 and 2 cancelled out, x upon r square. So r square can be written as x square plus L square by 4. So over here we can write r square equal to x square plus L square by 4. So this is the equation that we obtain for E net. Now the problem over here is asking us for maximum value of E. So we are writing for E net to be maximum, we put dE by dx equal to 0. So if we put dE by dx equal to 0, we have the term of x in both numerator and denominator. So over here we solve it in this way. So lambda upon pi epsilon naught taken out. So we differentiate x upon x square plus constant c, which is L square by 4, with respect to dx and equate it to 0. So we perform denominator square. So x square plus c whole square. So we will put denominator as constant and differentiate the numerator, and then subtracted by that we will differentiate the denominator keeping numerator constant and equate it to 0. So this is the expression that we have, and over here we can say 2x square minus 2x square plus x square plus c, where c being equal to L square plus L square by 4, this value is equated to 0. So we get the value of x as plus minus L by 2. So we get minus x square plus c, so x equal to c, and c being equal to L square by 4. So we get x equals plus minus L by 2. That is plus minus L by 2 is representing that on either side of the wire system we will have the maximum value of field, and hence if we put the value in this expression, we get E maximum value, and we get E maximum value as lambda upon pi epsilon naught L. So this is the final answer for the problem which we are discussing, problem 3.22.